Question 5. This question is about the chemical properties of chlorine, sodium chloride and sodium bromide. Sodium bromide reacts with concentrated sulfuric acid in a different way from sodium chloride. Write an equation for this reaction of sodium bromide and explain why bromide ions react differently from chloride ions. So you've got to learn the equation. So sodium bromide and concentrated sulfuric acid make something called sodium sulfate, bromine, sulfur dioxide and water. Sodium sulfate is NaSO4, Na2SO4, because SO4 is SO4 2-, and sodium's in group 1 forms a 1+ ion. A 1+ ion, you'll need two 1+ ions to balance out the 2- charges on the sulfate ion. And you just got to learn that it makes bromine and sulfur dioxide and water. Why does bromide ions react differently from chloride ions? It's because they're further down the periodic table, so they're bigger, they've got more shells, and if they've got more shells, the more easily they lose an electron more easily because they're larger. So the outer electron is lost more easily because there's more shielding and they're further away from the nucleus. The colourless solution contains a mixture of sodium chloride and sodium bromide. Use an aqueous silver nitrate and any of the reagents of your choice. Develop a procedure to prepare a pure sample of silver bromide from this mixture. So you've got a mixture of sodium chloride and sodium bromide, and you've got to try and make silver bromide from this mixture. Explain each step in the procedure and illustrate your explanations with equations where appropriately. So the first thing is to add the silver nitrate. You add the silver nitrate to the mixture, and it's going to make two precipitates. It will make silver chloride and silver bromide. Silver chloride is a white solid, a white precipitate, and silver bromide is a cream precipitate. And you can actually write the two equations of that to support that as well. So AgNO3 is silver nitrate, NaCl makes AgCl, and NaNO3 sodium nitrate. Silver nitrate and NaBr, sodium bromide, makes silver bromide and NaNO3, sodium nitrate again. Next, you've got to find a way of separating these two. So what you can do is you can add dilute ammonia. Dilute ammonia will dissolve the silver chloride, the AgCl, but it won't dissolve silver bromide. To dissolve silver bromide, you need to use concentrated ammonia. So dilute ammonia is going to dissolve this. If you dissolve it, the silver chloride dissolves. You can actually write an equation for that as well. AgCl plus NH3 makes AgNH3 twice, plus Cl minus, so you can need two NH3s. And next, finally, so you've got the silver bromide, which hasn't dissolved. You're going to filter it off, filter the precipitate off, wash it and dry it. Write an equation for the reaction between chlorine and cold sodium hydroxide solution. Give the oxidation states of chlorine and each of the chlorine-containing ions formed. So chlorine and sodium hydroxide, NaOH, would make NaOCl and NaCl and H2O. So if there are NAs there, it would be Cl2 plus NaOH makes NaOCl and NaCl plus H2O. But as an ionic equation, you don't involve the Na. You just Na is plus, so you'd have OH minuses, OCl minuses, ignoring the Na plus. This must be OCl minus. NaCl must be Na plus Cl minus. And then you're going to need two OH minuses to balance up the two O's and the two H's. What oxidation state is this in? Well, Cl is in -1. O is in -2. If there's one minus left over, that must be in +1, because -2 plus 1 leaves -1 left over, and Cl minus is just on its own, so that's in -1 oxidation. Question 6. A difficult question this, because you've got to work it out and talk about things theoretically. You've not got all of the numbers. You talk about how you would do it rather than come up with an exact answer. Anyway, this question is about calcium compounds. A pure solid is thought to be calcium hydroxide. Calcium hydroxide reacts with 2 moles of HCl hydrochloric acid. Makes calcium chloride and water. And then what you can do is you can take any unreacted acid. That gives you a clue. Unreacted acid, it means that we've got excess acid. We're going to use up all of the calcium hydroxide and we're going to have unreacted excess acid. That might be important. So the excess acid that you've got left over after the calcium hydroxide is reacted can be determined with titration with standard sodium hydroxide. So what you do is you take the leftover acid and you react it with sodium hydroxide. You know the concentration because you've made it up to a certain concentration of the sodium hydroxide, and you can work out the volume of sodium hydroxide that you've got to add from a burette. And knowing the concentration of the sodium hydroxide that you're using and the volume that you're using, you can work out the number of moles of sodium hydroxide that you need to add to react exactly with the HCl. Therefore, you can work out the number of moles of HCl that you've got reacting or left over, and therefore you can work out the number of moles of calcium hydroxide. That's the way it's going to go. Let's see it now in more detail. So you're provided with 50 centimetre cubed of 0.2 mole decimetre cubed hydrochloric acid. So first of all, before we go any further, let's work out how many moles that is. We've been given a volume, we've been given a concentration, so let's work out the number of moles that we've got. So what you do is concentration is moles divided by volume. Moles is concentration times volume. Concentration is 0.2. The volume is 50 centimetre cubed. We've got to get into decimetre cubed. A centimetre cubed up into a larger unit value, decimetre cubed, you divide by 1,000. So it's 0.2 multiplied by 50 divided by 1,000, 0.01. That's the number of moles of acid that we've got. So experimentally, how much calcium hydroxide would we use? 1 mole of calcium hydroxide reacts with 2 moles of acid. So if we take that number and we divide by 2, that comes out as 0.005. 0.005. Now, how many grams of calcium hydroxide are we going to need? It doesn't tell you, so let's work it out. So the MR of calcium hydroxide is 74, so it's 40, add 2 16s for the oxygens, add 2 1s for the H's, it comes out as 74. Mass is 0.005 times 74. It comes out accurately as 0.371. That's number of grams of calcium hydroxide that would react with 2 moles of acid. However, in the question it says that you've got any excess acid, any leftover acid. So we've got acid in excess. So that amount of calcium hydroxide would use up all of the acid, so we need something less than that, less than 0.371 grams. Anything less than that would leave some of the acid left over. The next stage then is you've got to get this leftover acid. You get the leftover acid and you measure it out. So we're going to measure it out 50 centimetre cubed using a pipette. And add the weighed amount of solid to the conical flask. So you get 50 centimetre cubed of the acid that you've got here. It says you provide with 50 centimetre cubed. Let's use a pipette. Let's do it accurately. 50 centimetre cubed using a pipette, and you add the calcium hydroxide. Okay, and then the leftover acid you're going to titrate against sodium hydroxide. It says a standard solution of sodium hydroxide. Now when you titrate anything, you usually use 0.1 as a concentration. So 0.1 is going to be the concentration of sodium hydroxide that you're going to add. And you have the sodium hydroxide in a burette and you'll be adding it. You'll have the leftover hydrochloric acid in a conical flask that you've mixed with the calcium hydroxide, so you'll have that underneath. You'll have to add an indicator. The best indicator to use, incidentally, is phenolphthalein. Phenolphthalein, it means that when the sodium hydroxide just reacts with the hydrochloric acid and then you add one more drop of sodium hydroxide, the phenolphthalein in excess sodium hydroxide goes a nice pink colour. So phenolphthalein is good to use if you're adding sodium hydroxide from the burette. And so you can titrate it. Now this is the complicated bit. How are you going to work out the relative formula mass of the solid? So that you've added the calcium hydroxide to work out whether it is indeed calcium hydroxide, because they think it's calcium hydroxide, they're not sure. If they can work out its MR, then they can prove almost, I suppose, that it's calcium hydroxide that they've got there. So how do you work out the MR from this experimental data? Well, from my titration, I've just added sodium hydroxide. I know the volume of sodium hydroxide that I need and I know its concentration. So For sodium hydroxide, concentration is moles divided by volume, so I can rearrange that so moles equals concentration times volume. I know the concentration of my sodium hydroxide because I made it up to a certain concentration and we're suggesting 0.1. We know the volume that we've had to add from the burette, so we know the number of moles of sodium hydroxide. Now, sodium hydroxide NaOH reacts with HCl. 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid, and it's going to make NaCl and water. So the number of moles of sodium hydroxide that I've just worked out that I've got is equal to the number of moles of HCl that's left over in this reaction. Let's call it X. Let's just call it a value X. So the moles of HCl that have reacted, the moles of HCl that are unreacted is X. The moles of HCl that are reacted are however many I started with. The number of moles of acid was 0.001. Take away X. So that's the number of moles of acid that have reacted. That's the number of moles of acid that are left over. I started with 0.1. I've got 0.01 moles of acid. I've got X number of moles left over. So the amount that I've actually reacted is 0.01 take away X. Now, hydrochloric acid, 2 moles of hydrochloric acid react with 1 mole of calcium hydroxide. So the moles of calcium hydroxide that I've reacted is 0.01 take away X, the number of moles of hydrochloric acid, divided by 2. And when you get the number of moles of calcium hydroxide, Mr is mass multiplied by moles. You've got the mass. The mass that you've used was 0.371 or slightly less than that, but you know it's mass, you know how much you've added. Mass divided by moles will give you the Mr, and hopefully if it is calcium hydroxide then it will turn out to be around 74. A 3.56 sample of calcium hydroxide was dissolved in water and reacted with an excess of sulfuric acid to form calcium sulfate. The percentage yield of calcium sulfate was 83.4. Calculate the mass of calcium sulfate formed. Give your answer to an appropriate number of significant figures. Well, these are to 3 significant figures, so we better put it to 3 significant figures. Let's have a look then. The moles of calcium hydroxide. So, I've got 3.56 grams of calcium chloride. So I could work out the Mr of calcium chloride. I've got calcium chloride here in my previous equation if I wasn't sure, CaCl2. So that's a 40, add 2 35.5s, and so I know it's 111.1 is the Mr of calcium chloride. So moles is mass divided by 111.1. 3.204 times 10 to the minus 2 is the number of moles of calcium chloride. The number of moles of calcium sulfate that I would make is exactly the same, because calcium chloride then reacts to make calcium sulfate, and 1 mole of calcium chloride will make 1 mole of calcium sulfate. So the number of moles of calcium sulfate is exactly the same, 3.204 times 10 to the minus 2. However, I've only got a percentage yield of 83.4%. I've lost some of it along the way. So the actual number of moles is 83.4 divided by 100. That's a fraction. So it's a percentage as a fraction. Multiply, I actually make 2.672 times 10 to the minus 2 moles of calcium sulfate, because some of it has been lost along the way. The mass of calcium sulfate. So the mass of calcium sulfate is the number of moles multiplied by the Mr of calcium sulfate. I'd have to work that out. It's CaSO4, so a 40, add a 32 for the sulfur, add 4 16ths for the oxygens, 136.2, and it comes out as 3.6398, but I want it to 3 significant figures because the other values are to 3 significant figures in the question. Question 7. A sample of pure magnesium nitrate was decomposed by heating as shown in the equation below. 2 moles of magnesium nitrate makes 2 moles of magnesium oxide, 4 moles of nitrogen dioxide gas and 1 mole of oxygen gas. A 3.74 times 10 to the minus 2 gram sample of magnesium nitrate. Why have they given me mass? They've given me mass and they've given me a formula, because from the formula I can work out Mr, and using the mass and the Mr I can work out number of moles. So let's do that first of all. So Mr of magnesium nitrate, I've got an Mg which is a 24, Inside the bracket I've got one N and 3 O's, but everything's multiplied by the number outside the bracket. So I've got 2 N's and 6 O's. So I've got a magnesium with a mass of 24, 2 14s for the nitrogens and 6 16s for the oxygen at 148.3. Moles is mass divided by MR, so 3.74 times 10 to the minus 2, which is the mass of the sample, divided by 148.3, 2.522 times 10 to the minus 4. Now, why have I been given R? R only appears in PV equals nRT. So PV equals nRT is my gas equation. It concerns itself with gases. And N in there, PV equals nRT. The N is the number of moles of gas. So how can I work out the number of moles of gas? Well, I've made 4 moles of gas here and another 1 mole of gas here. 4 moles of nitrogen dioxide and 1 mole of oxygen. I've made 5 moles of gas. It doesn't matter for the gas equation what kind of gases you've got as long as they're gases. So I'll make 5 moles of gas. 2 moles of the magnesium nitrate make 5 moles of gas. So 1 mole of magnesium nitrate, half the amount, would make 2.5 moles of gas. So 2 make 5, 1 would make 2.5 moles of gas. I've got 2.522 times 10 to the minus 4 moles of magnesium nitrate. 1 would make 2.5, so 2.522 times 10 to the minus 4 multiplied by 5 over 2, or 2.5, equals 6.305 times 10 to the minus 4. I now know the number of moles of gas. So for PV equals nRT, that's N. Okay, let's have a look at these other things then. PV equals nRT. P is pressure. Pressure needs to be in pascals. It's in kilopascals. To turn a large unit value like kilopascals down into a smaller one like a pascal, I multiply by 1,000. So 100 kilopascals is 100,000 pascals. N I've just worked out as 6.305 times 10 to the minus 4, or 0.000630. Temperature is 60 degrees C. It needs to be in Kelvin, so to convert degrees C into Kelvin, add on 273. That works out as 333. I think I'm now ready to do PV equals nRT. I've not got V, that's what they want me to work out. So PV equals nRT. P is 100,000 pascals. V I don't know, they want me to work that out. N is the number of moles, 0.006305 or 6.305 times 10 to the minus 4. 8.31 is my gas constant. R, temperature is 333. So V is all of this divided by 100,000. So on the top here it comes down to the bottom, divide by 100,000 on the other side, and it comes out as 1.745 times 10 to the minus 5 meters cubed. Now to get meters cubed into centimeter cubed, like they asked me to, they want me to the total volume in centimeter cubed, you've got to convert units twice. Meters cubed down into a smaller unit, decimeter cubed, and multiply by 1,000. So that works out as 1.745 times 10 to the minus 2. And then to get decimeter cubed down into another smaller unit value of centimeter cubed, I multiply by 1,000 again, 17.45. So meters cubed into decimeter cubed are multiplied by 1,000. Decimeter cubed into centimeters cubed and multiply by 1,000 again. So every time I go from a large unit value down into a smaller unit value, I multiply by 1,000. So 1.745 times 10 to the minus 5 multiplied by 1,000 gives me decimeter cubed, multiplied by another 1,000 gives me centimeter cubed, 17.45. However, it says to the appropriate number of significant figures. If you look at all of these, they're all to 3 significant figures. So let's round this up. I could round it up or down. I always prefer to round up. 17.5 centimeter cubed, 3 significant figures. 7.2. The mass of magnesium oxide explained in this experiment is slightly less than I expected. So why do you get less than 100% yield? You're going to lose some of it when you're weighing it out or making it. So some of it is lost. Some of the solid is lost when you're weighing out the product or before you weighed the product out. So whilst you're making it, you've lost some of the magnesium oxide. Question 10. Which of these pieces of apparatus has the lowest percentage uncertainty in the measurement shown? So let's have a look. We've got a volume of 25 centimeter cubed being measured out on a burette. Remember, a burette, you take a reading at the start and the end, so you take 2 readings. Each reading has an uncertainty of plus or minus 0.1 centimetre cubed. So you take 0.1, which is the error, you multiply by the number of readings, which is 2, because 2 readings, each with a 0.1 centimetre cubed uncertainty, could then have an uncertainty of twice that value, 0.2. So you take the 0.1, you multiply by 2, because there's 2 readings. You divide by the volume that you're measuring out, and you multiply by 100. So it's the error divided by the volume, or the measurement that you're taking, multiplied by the 100. So 0.1 times 2 divided by 25 multiplied by 100%. So let's have a look at the next one, a measuring cylinder. Well, you only measure once on a measuring cylinder, and there's an error of 0.5 divided by the volume, which is 25. So it's 0.5 multiplied by 1 multiplied by 100% divided by 25. 0.15 grams measured out with a balance. Again, you only measure once on a balance with an uncertainty of 0.001. So it's 0.001 multiplied by 1 multiplied by 100% divided by 0.15. Temperature change. So this time we've got a temperature change 23.2. Now there's a temperature change, so that implies that you're measuring the temperature at the start and at the end and working out the change. So you're going to be measuring the temperature with a thermometer twice. So it's 0.1 multiplied by 2, because you're taking 2 readings, multiplied by 100% divided by 23.2. And the lowest value is the top one. The answer is A. A student is provided with 5 centimetre cubed sample of 1 times 10 to the minus 2 mole to the decimeter cubed hydrochloric acid. Right, I've got a volume and I've got a concentration, so immediately I know what I'm going to have to do. I'm going to work out number of moles. Concentration is number of moles divided by volume in decimeter cubed, so 1 times 10 to the minus 2 is number of moles divided by this. I've got to get this 5 centimetre cubed divided by 1,000 though, so it's 0.005. So concentration is 1 times 10 to the minus 2 divided by 1 times 10 to the minus 2, which the concentration is moles divided by 0.005. Number of moles is 0.005 multiplied by the concentration. Multiply these two numbers together, divided by 1,000, equals the number of moles. I'm going to have to do that first. Okay, so 0.01, which is my moles of hydrochloric acid, equals the moles divided by 0.005. Moles of these two multiplied together, 0.00005. That's the number of moles of hydrochloric acid that I've got. Now I'm going to have to work out how much water I'm going to have to add to get the concentration to be 5 times 10 to the minus 4. So I'm changing the concentration by adding water. So the new concentration is 5 times 10 to the minus 4, or 0.0005. Equals the number of moles, because the number of moles haven't changed from the first bit. I'm only about to add some water. The number of moles of hydrochloric acid has stayed the same, 0.00005 divided by volume. So the new concentration equals the number of moles that I've worked out divided by the volume. The volume is 0.0005 divided by 0.005, 0.1. Now that's in decimeter cubed. To get decimeter cubed down into a lower unit value of centimeter cubed, I multiply by 1,000, 100 centimeter cubed. So I've got to get the volume to be 100 centimeter cubed. I've already got 5 centimeter cubed of water in there, or 5 centimeter cubed of solution. I've got to get the new volume to be 100 centimeter cubed. Therefore, I'm going to have to add a further 95 centimeter cubed. So they've put 100 centimeter cubed in there to try and fool you. It's 95 centimeter cubed because you've already got 5 centimeter cubed and you've got to make it up to 100 centimeter cubed. Which of these species has a trigonal planar structure? Well, let's work it out. Phosphorus is in group 5, so it's got 5 electrons in its outer shell, 3 hydrogens, 3 bonding pairs. That leaves 3 of the electrons are bonded. Out of the 5, there's 2 left over, or 1 lone pair. So there's 1 lone pair and 3 bonded pairs. It would be you'd try and put it in a tetrahedral shape, because there's 4. There's a total of 4 bonded pairs add lone pairs. So when you have lone pairs add bonded pairs together and it equals 3, then it's going to be planar. Anything more than 3, it's going to be 4. So you've got 1 lone pair and 3 bonded pairs. 1 add 3 is 4, so it's not going to be planar. That's usually the case for most species, apart from something like xenon tetrafluoride. So it's not planar. Okay, So that one's wrong. Let's try and work out what it is. If it's got one lone pair and 3 bonded pairs, you'd expect it to go into tetrahedral, but it's not tetrahedral because you don't see the lone pair. So it's not 109.5, that would be something like CH4, which would be tetrahedral. It's only got 3 bonded pairs and 1 lone pair, so you don't see the lone pair, you see the 3 bonded pairs, and the bond angle comes down from 109.5. Every lone pair you put on there onto a tetrahedral shape, then it lowers the bond angle by 2.5, so 109.5 take away 2.5 is 107, and you'll see the 3 bonding pairs in a trigonal pyramid shape. Okay. BCl3 has 3 bonded pairs and no lone pairs because it's in group 3, so it's got 3 bonded pairs, no lone pair. Now that might be planar. So 3 bonded pairs, no lone pairs will repel and repel equally to give a bond angle 120 in a trigonal planar shape. So your answer is B. Let's just check through C and D. C, oxygen has got 6 electrons in its outer shell. It's lost 1 because it's come plus, so it's got 5, 3 bonded pairs, 1 lone pair. Again, it's going to be the same shape as pH3 and CH3 minus. C is in group 4, gain 1 electron, so got 5, 3 bonded pairs, 5 electrons, 2 remaining as a lone pair is 3 bonded pairs and 1 lone pair. So you've got a trigonal pyramid in A, C and D, but because BCl3 hasn't got a lone pair of electrons, that's going to be your planar shape. Use your understanding of intermolecular forces to predict which of these compounds has the highest boiling point. So in terms of highest boiling point, I'm looking for something with a hydrogen bond that have the highest boiling point. Then I'd be looking for something that's polar, that's going to have dipole-dipole attractions. And then I'd be looking for van der Waals forces, something with no polar bonds within it, and therefore no dipole-dipole attractions, just van der Waals forces as the weakest and the lowest boiling point. So for hydrogen bonds, I'm looking for a hydrogen bonded to an oxygen, a fluorine or a nitrogen. I've got a hydrogen bonded to a fluorine here, so that's got hydrogen bonding, so that's my obvious choice. Hydrogen bonded to a Cl, well Cl is electronegative, so going to have a slight delta minus, and the H will have a slight delta plus, so that'll have polar dipole-dipole attractions between the bonds. Br is slightly electronegative, so it'd have a slight delta minus and a delta plus, and so would Hi. I is electronegative, so would have a slight delta minus and leave the H as delta plus. So B, C and D have all got dipole-dipole attractions, so medium sort of boiling points. HF has got the highest boiling point because it's got large delta plus and delta minus, large polar bonds between the H and the F, and therefore hydrogen bonds between the molecules, because the polar bond, the delta plus and delta minus, is so large because F is very electronegative compared to the H. So if you've got an H bonded to an F, an N or an O, you've got hydrogen bonding. The answer is A. Which type of bond is formed between N and B when a molecule of NH3 reacts with a molecule of BF3? Well, NH3, N is in group 5, it's got 5 electrons in its outer shell, it's got 3 bonding pairs, it's got a lone pair left over. After the 3 bonded pairs, 3 electrons go into the bonded pairs, because it's got in group 5 and got 5 electrons, it's got a spare pair of electrons, it's got a lone pair of electrons. The BF3 hasn't got any electrons left over because it's in group 3 and it's got 3 bonding pairs and they're all involved in bonding. So the nitrogen's got a lone pair. The boron, the B, hasn't got any electrons to put into a bond, so the nitrogen puts both electrons into the covalent bond. That's called a coordinate or a dative bond, where the covalent bond is set up, is created when both of the electrons come from one of the atoms rather than 2 atoms each putting 1 electron in each. Which of these atoms has the highest electronegativity? Well, I'm just looking down the list. You've got sodium and magnesium in group 1 and group 2 respectively, wanting to lose 1 electron and lose 2 electrons. Argon is in group 0, group 8, it's got a full outer shell, doesn't want to lose or gain any. Chlorine's in group 7, wants to gain 1 electron. So electronegativity is the power to withdraw electrons towards itself. So your answer is C. It wants to gain 1 electron with it being in group 7, only needing 1 electron to fill its outer shell. Which of these atoms has the smallest number of neutrons? So what you do is, for neutrons, you take the mass number, the top number, and you take away the bottom number, the proton number, or the atomic number as it's sometimes called. You'll have to look these up. Top number, the mass number is 3 for hydrogen, it's 1 is the atomic number, so 3 minus 1 is 2. 4 take away 2, helium has got a proton number of 2, so 4 take away 2 is 2. Helium 5 take away 2 is 3. Lithium has got an atomic number or a proton number, whichever way you want to call it, of 3, so 4 take away 3 is 1, so your answer is D. 17. Which of these substances does not show hydrogen bonding? So we've talked already about the fact that hydrogen bonding needs a hydrogen bonded to an F, a hydrogen bonded to an N, or a hydrogen bonded to an O. So we're looking for anything that doesn't have a hydrogen bonded to an F, a hydrogen bonded to an N, or a hydrogen bonded to an O. We've got hydrogen bonding to an F, so A does have hydrogen bonding. We've got NH3, nitrogen bonding to 3 hydrogens, so that one does. We've got CH3CO, that's a C double bond O, but then we've got an O bonded to an H, so we've got an H bonded to an O there, so that does. This one doesn't have any hydrogens bonded to F's, N's or O's. The CHF3 has got a carbon bonded to an H and a carbon bonded to 3 F's, so your answer is D, with no hydrogen bonded to an F, an N or an O. What is the formula of calcium nitrate? Calcium is in group 2, so going to form 2+. You need to know that a nitrate ion is NO3 minus, and the whole ion is a minus ion. So it comes all together as NO3 minus. So calcium is Ca2 plus NO3 1 minus. I need 2 NO3s, and the whole thing comes together. So as a whole ion, and NO3 minus ion, so I need 2 of those. 2 1 minuses to balance the 2+ here. Another way of looking at it is that the nitrate ion is the nitrogen is in group 5, is in oxidation state 5. So calcium is in group 2, that's 2. 3 minus 2's for the oxygen, because oxygen is in oxidation state -2. It's in group 6, gains 2 electrons, so it's in -2 oxidation state. So 2+ and 3 2 minuses is 6 minus, 2+ and 6 minus, no charge left over. That nitrogen's in oxidation state 5. What have I got here? I've got calcium in 2, I've got 2 times 3 is 6 oxygens, each oxygen in -2 oxidation state is -12, plus 2 is 10, and I've got 2 nitrogens, so 10 divided by 2 is 5. That nitrogen's in oxidation state 5. Let's check this out then. Calcium, 2 of them, each in 2+ oxidation state, they're in +4. Nitrogen the oxygen is in -2, so that nitrogen is in oxidation state 0 in actual fact. Calcium NO2 twice. Calcium is in group 2, so 2+ oxidation state. 4 oxygens each in -2 oxidation state is -8. Calcium is in +2, so that leaves +6. The nitrogen is in +6. So you could have worked it out from that 5 there that it's B. Or you could just know that nitrate ion is got a 1 minus ion. You'll need 2 of them to balance out the Ca2+. Which of these elements has the highest second ionization energy? Well, I'm going straight away for sodium, for the simple reason that sodium's in group 1, loses 1 electron, and the second electron would have to come from a full stable shell underneath. Question 20. Which of the following shows chlorine in its correct oxidation state in the compound shown? So I've got HCl. Hydrogen is usually +1, so +1 means that the Cl would be -1, because +1 -1 leaves no charge left over. So the Cl is in -1, so immediately I'm drawn to either A or C. Potassium's in group 1, so it's +1 oxidation state. Oxygen's in group 6, so gains 2 electrons to fill its outer shell, they're -2 each. +1 and 6 -2's, 3 -2's, Plus 1, 3 minus 2 is minus 6, plus 1 minus 6 is plus 5. So yes, we're going to go with C. Let's just check the last one. Plus 1 for the hydrogen, minus 2 for the oxygen, plus 1 minus 2 is plus 1 for the Cl to leave no charge left over. So we're going with C. So C is the definite answer. The substance is not produced in a redox reaction when solid sodium iodide reacts with concentrated sulfuric acid. Well, you've got to know this reaction, you've got to learn it. There's some learning to be done here. Sodium iodide and concentrated sulfuric acid makes hydrogen sulfide, smells of bad eggs. Sulfur dioxide, which is the acidic gas responsible for acid rain. Iodine, I2, and something called sodium hydrogen sulfate. So the only one that's not produced is HI. All of the other three are. There's a little bit of learning to do there. Which of the following contains the most chloride ions? Well, first of all, you're given a volume and a concentration for each of these. So what you need to know is that concentration is volume, moles divided by volume, and you've got to convert these volumes into decimeter cubed. So let's take the first one, say for example. So we take concentration, moles is concentration times volume, concentration is moles divided by volume, so you could rearrange that to be moles is concentration multiplied by volume. So the number of moles is the concentration that we've got here, 3.3 times 10 to the minus 2, or 0.33. 0.033. You've got to divide the 10 centimeter cube by 1000 to get it into decimeter cube, multiply the two together and I get 0.00033. I'll come to the multiply by 3 in a minute. You do the same for all of the others, so 20 divided by 1000 to get that into decimeter cube, multiplied by the concentration gives the number of moles. I'll come to the times 2, multiplied by 2 in a minute. 30 and 3.3 times 10 to the minus 2. 30 divided by 1000 to get 30 centimeter cubed into decimeter cube multiplied by the concentration, and same for D, 40 divided by 1000 multiplied by 0.025. Okay, so why have these two got a multiply by 3 and a multiply by 2? Well, you need to know the formula of each of these. Aluminium chloride, Al is in group 3, so going to form 3 plus ions because it'll lose 3 electrons. If it's in group 3, it's got 3 in its outer shell, wants to lose 3, so it'll become 3 plus. Cl is in group 7, so it wants to gain 1 electron, so it'll form Cl minus. So you've got Al3 plus Cl minus. You need 3 minuses to balance out the 3 pluses on the aluminium. So aluminium chloride is AlCl3. So when it dissolves in water, it's going to make 3 moles of chloride ions from 1 mole of aluminium chloride. That's why you've got to multiply by 3. Calcium is in group 2, chloride is in group 7, so that's going to be plus 2 minus 1, so it's going to be Ca2 plus Cl minus, but you'll need 2 Cl minuses to balance out the 2 plus. So you've got 2 chloride ions in calcium chloride, so 1 mole of calcium chloride would make 2 moles of chloride ions, so you need to multiply by 2. Hydrochloric acid is just HCl, sodium chloride is just NaCl, so I've got 1 Cl in each of those. That's why you just multiply by 1 or leave them alone. And so my answer is B. Which one of the following contains the most? Which one's the largest value of them all? Is B. Question 8 and 9. Which of these atoms has the largest atomic radius? Well, they're all atoms in period 3, so as you go across period 3 you've got sodium, then you've got magnesium, and then further across you come to chlorine and argon. So they've all got the same number of electron shells. As you go across the period from left to right, so you go from sodium to magnesium, then to chlorine, then to argon, they're getting more and more protons. So as they get more and more protons, they're getting more and more nuclear attraction, they're getting smaller. So as you go right across a period, the atomic radius gets smaller and smaller and smaller. So the radius is the distance from the nucleus to the outer electron. It's getting smaller and smaller and smaller because they're getting more and more protons as you go left to right across the period. So sodium is going to be the smallest with the fewest number of protons, and so the lowest nuclear attraction for the electrons. That's going to have the largest atomic radius. They get smaller and smaller and smaller as you go across to the right hand side. Which of these species is the best reducing agent? Now remember what a reducing agent does. A reducing agent causes something else to be reduced. So if something else is going to be reduced, One of these is going to be oxidized. So something that's oxidized makes something else reduced. So something that's oxidized is a good reducing agent. So which one of these is going to be oxidized? So the best reducing agent is which one of these is going to be best oxidized. Now what's oxidation? Oil rig. Oxidation is loss, reduction is gain. Oxidation. So which of these is going to go through oxidation? Oxidation is loss. Which one's going to lose electrons? Well, I'm going to go for either B or D for a start because they've got an electron ready to lose. And which one is going to lose it most readily? Iodine, because it's further down the periodic table, it's bigger, and that electron that it's ready to lose is further from the nucleus, more shielding, less nuclear attraction, with it being further away from the nucleus. The answer is D. AS Chemistry, Paper 1, Specimen 0.5. Use the periodic table to deduce the electron configuration of calcium. Well, calcium's got an atomic number or a proton number of 20, so it's got 20 electrons. So it'll go 1s2, 2s2, 2p6, 3s2, 3p6, and then it'll have 4s2 electrons in its 4s2 in its fourth shell. So it's got 2 electrons in its outer shell in group 2. Write an ionic equation with state symbols to show the reaction of calcium with an excess of water. Well, calcium will react with water to make calcium hydroxide and hydrogen gas, because calcium is a metal. So a metal reacts to make the metal hydroxide and hydrogen gas. But if it's an ionic equation, you'll want to draw or write down calcium as Ca2+, because calcium's in group 2 of the periodic table, so loses 2 electrons, and hydroxide are OH- ions. So you've got calcium plus H2O goes to Ca2+, which is a calcium ion, OH- ions, which are the hydroxide and the hydrogen gas. You're going to need you're going to have 2 OHs to make 2 O's, 2 O's, 4 H's, 2 add 2 is 4, and the 2 plus and the 2 minuses cancel each other out and make no charge on the right hand side, no charge on the left hand side. State symbols then: calcium's a solid, water's a liquid, these ions dissolve so they're aqueous, and hydrogen's a gas. State the role of water in the reaction with calcium. It's an oxidizing agent because it's turned calcium from oxidation state 0, an element on its own is oxidation state 0 with no charge, to 2+, so it's gone up, it's gone from 0 up to +2, the oxidation state has increased, it's been oxidized. And the water's done the oxidizing, so that's the oxidizing agent causing the other reagent to be oxidized. Write in the equation to show the process that occurs when the first ionization energy of calcium is measured. So you've got calcium, it's got to be a gas, loses an electron to form a 1+ ion. So calcium gas loses an electron, there's the electron that's lost, and it's still as a gas, and it forms 1+ ion because it's lost 1 electron. State and explain the trend in the first ionization energy of the elements in group 2 from magnesium to barium. Well, they get smaller. The reason they get smaller is because the ions are getting bigger. They're getting larger and larger and larger as you go down the group, or you could say they're getting more shells. And what's happening is that as they're getting bigger and bigger and bigger, then the nucleus is further away from the outer electron, so the electron is lost more easily. The nuclear attraction is less because the nucleus is further away. It's also because there's more shielding as well, because it's got more shells, electron shells, so they will shield the attraction from the nucleus to the outer electrons. So you could summarize all that by saying there's a weaker attraction of the ion to the electron that's being lost. Question 2. A sample of sulfur consisting of 3 isotopes has a relative atomic mass of 32.16. Table 1 gives the relative abundance of 2 of these isotopes. So that means 91.0% has a mass of 32, has atoms of a mass of 32. 1.8% has atoms of a mass of 33. Use this information to determine the relative abundance and hence the mass number of the third isotope. So there's a third one that's missing. Give your answer to the appropriate number of significant figures. So now we've got to work out what mass the third one has and also what abundance it has. Well, there's only 3 isotopes, so if one of them, if the atom's 32, the isotope with a mass number of 32 is 91%, and this one's 1.8%, then 100% take away 91, take away 1.8% will tell you that 7.2% is the remaining isotope. So 7.2% is this remaining isotope, and we don't know what mass it is. We know that the average is 32.16. So what we've got to do is imagine there's 100 particles. 91 particles have got mass 32, 1.8 particles have got mass 33, and the remaining, which is 7.2 particles, have the mass whatever that is. So the mass of these particles of mass 32, there are 91 of them out of 100, so 91 particles, each mass 32. We'll work out the mass of those together. There are 1.8 particles mass of 33, so 33 multiplied by 1.8 is the mass of these particles, and there are 7.2 particles of mass that we don't know. Let's call it y. If we divide by the total number of particles, and there's 100 particles, this will give us the average, which equals 32.16. Multiply both sides by 100, or so you can multiply both sides by 100 and then work out these values. 32 multiplied by 91, 33 multiplied by 1.8 will plus y times 7.2, 7.2y will equal 3216. Take these values across to the other side, and 7.2y will equal 32.16 multiplied by the 100. Take away 32 times 91, take away 33 times 1.8, because these are coming across to the other side, so they're going from positive to negative, and that equals 244.6. Divide both sides by 7.2, so y is 244.6 divided by 7.2, 33.96. It's got to be two significant figures. It's got to be a whole number essentially, because isotopes can't have odd numbers, so we'll round it up to 34. So its mass number is 34. Describe how ions are formed in a time-of-flight mass spectrometer. Well, they're bombarded with something called an electron gun, and the electron gun removes electrons from the atom. So the electron gun, which fires electrons at the particles, then hits the particles and removes an electron from the particle. The electron gun fires out high energy electrons, so fast moving electrons. So you hit the sample, the atoms in the sample, by high energy electrons fired from an electron gun, and then the sample loses an electron, forming an ion or a particle with a plus charge. We've called the particle M here. But it's essentially a particle that's lost an electron and having a plus charge. The time-of-flight mass spectrometer can be used to determine the relative molecular mass of molecular substances. Explain what is necessary to ionize, in other words, turn the particles into plus ions when measuring their mass in a time-of-flight mass spectrometer. Well, you need to accelerate them. So what you have is you have plates with small holes in them that are negatively charged, and the plus charged particle that you've just made is accelerated these plates. It goes through the plate and then hits a detector. When the plus charged particle hits a detector, it turns back into an atom, so the plus charged particle gets its electron back off the detector plate and forms atoms, and that generates an electric current that we can read. So ions, so plus charged particles, not molecules, will interact with and be accelerated by the electric field. So these plates, charge minuses, accelerate the ions towards them down the tube. And the ions create a current when hitting the detector. So the way that works is the plus charged ion gets an electron back from the detector plate, and to form atoms rather than ions. So it gets its electron back and loses its plus charge. And in doing so, it creates a current, and then we can read that from the detector. Question 3. Write an equation including state symbols, so that's S for solid, L for liquid, G for gas, AQ for aqueous or dissolved in water, for the reaction with the enthalpy change equal to the standard enthalpy of formation of CF3 gas. So Enthalpy, standard enthalpy of formation is where you make 1 mole of a substance from the elements in their standard states. The standard states is how you'd normally find them in a lab under laboratory conditions of temperature and pressure. So we're making 1 mole of CF4. What will we make it from? We'll make it from carbon and fluorine. Carbon, C, is a solid, and F, fluorine, is F2. We're going to need 2 moles of F2, and that's a yellow gas. Explain why CF4 has a bond angle of 109.5. Well, carbon's in group 4, so it has 4 electrons in its outer shell. If 4 Fs come and bond with covalent bonds, those 4 electrons, carbon's going to have 4 bonding pairs, and it's got no leftover electrons, so it's going to have no lone pairs. It's got 4 bonding pairs. These will repel equally and as far apart as possible and form a bond angle of 109.5. It will form a tetrahedral shape. So around carbon there's 4 bonding pairs of electrons. These repel equally and spread as far apart as possible. You don't even need to mention it's in a tetrahedral shape. We've got some standard enthalpies of formation here of each of these chemicals, but we haven't got C2H6, and it's asking us to work that out. So what you need to know is that the enthalpy change, the overall enthalpy change, which is given here, delta H, is minus 2889. That equals the enthalpies of the products, so 2CF4 and 6HF, those two added together on the right hand side, subtract the enthalpies of formation of these two, so 1 C2H6 and 7 F2. We don't know the C2H6, it's not given to us, so that's what we've got to work out. So minus 2889 equals 2 CF4, so that's 2 multiplied by 680 minus 680, 6HF minus 269 multiplied by 6. Take away the enthalpies of formation of the reactants, those on the left hand side. 7F2, F2 is 0 because it's an element, it's already as an element, so there's nothing to form there, so that's 0. Take away the enthalpy of formation of C2H6, which we haven't got, so we'll call that X. So we take away 7 zeros, which we can leave out, take away X, which is going to be the value of the enthalpy of formation of C2H6. The easiest way of doing this is minus X, take that across to the other side, it becomes plus X, minus 2889, take this across to the left hand side, it becomes plus 2889. So X equals plus 2889, take away 2 times minus 680, which is minus 360. 6 times minus 269 is 1614. It equals, X equals minus 85. And it's in kilojoules per mole, because the other values are in kilojoules per mole as well. Methane reacts violently with fluorine according to this equation, some mean bond enthalpies. Now bond enthalpy is slightly different. I always think burp, B-E-R-P, burp. Bond enthalpy is reactants take away products. It's the other way around really from enthalpy. Reactants take away products. So we add up all the bond enthalpies of the reactants and we then subtract the enthalpy of the bond enthalpies of the products, and that equals the overall bond enthalpy, which is my delta H. So let's have a look. The bonds broken, i.e. the left hand side, the reactants, I've got CH4, I've got 4 lots of CH in CH4, so I've got 4 lots of CH. I've got 4 lots of FF or F2. Okay, so that equals 4 times 412 plus 4 times F2. I've not been given F2, that's what I've got to work out. The bonds form, so on the right hand side, 4 CFs, 4 HFs. So that's 4 times 484, which is a CF, and 4 times 562, which is a HF. And remember what I said, bond enthalpy, or delta H minus 1904, equals the bonds broken, or the reactants, burp, bond enthalpy, reactants, take away products, reactants or bonds broken here is this value, 4 times 414 plus 4 times F2F that we don't know, take away the products or the bonds formed, minus take away 4 times 484 and 4 times 562. So when we rearrange it, 4 lots of F2F, okay, equals minus 194. Take away 4 times 19412 because I've taken it to the other side, so it's gone from plus to minus. And then the minus values here become plus on the other side, so they go plus equals, and all of that equals 632. So FF is 632 divided by 4, so 4 of them equals 632, so one of them is 632 divided by 4, 158. Is the student correct? The student suggests that one reason for high reactivity of fluorine is a weak F2F bond. Is the student correct? Justify your answer with calculation. The student's correct because the FF bond is much less than the CH or the other covalent bonds, therefore the FF bond is easily broken. 158 seems to be much less than the other bond enthalpies in the question. Question 4. Colour solutions of X and Y react to form an orange solution of Z according to the following equation. 1 mole of X and 2 moles of Y makes 1 mole of Z. A student added a solution containing 0.5 moles of X to a solution containing 0.5 moles of Y. After 30 seconds there was no further change in colour, probably because the reaction is finished then. The amount of Z at equilibrium was 0.2 moles. Deduce the amounts of X and Y at equilibrium. Well, you're best setting it out like this. Write the equation out, and underneath each one, underneath of X and Y and Z, put the amounts at the start. So there's 0.5 moles of X, 0.5 moles of Y, and no moles of Z yet. Then you mix them, and you work out how much is formed or how much is used up. It tells you that 0.2 moles of Z is made. Now 1 mole of X makes 1 mole of Z, so 0.2 moles of X would make 0.2 moles of Z. In other words, 0.2 moles of X would be used up. 2 moles of Y makes 1 mole of Z, so 2 times 0.2, which is 0.4, 0.4 moles of Y would make 0.2 moles of Z, so 0.4 of Y is used up. So how much is then at equilibrium? Well, you start with 0.5 moles of X, you've used up 0.2, you've got 0.3 left over. Y, you started with 0.5, you used up 0.4, you've got 0.1 left over. Z, you didn't have any to start with and you've made 0.2, so you've got 0.2. On the grid below, draw a graph to show how the amount of Z changed from the time of initial mixing until 60 seconds had elapsed. Okay, so what you've got to do is you've got to label each axis. So you've got to label this one moles of Z, going up to 0.2. So start at 0, maybe go 0.05, 0.1, 0.15, 0.2, maybe 0.25, something like that. And then along the bottom it says for 60 seconds. So you're going to go 10, 20, 30, 40, 50, 60 seconds. And then you're going to draw a graph, and the graph will increase and it will go up to 0.2. So if you've got 0.05, 0.1, 0.15, 0.2, let's say, it's going to come up to here after 10, 20, 30 seconds. It's going to hit that point there and then it's going to level off. So it'll go through 0, it'll come up and it'll start to level off, and at that point there, which is 0.2, it's going to flatten off. The student prepared another equilibrium mixture in which the equilibrium concentrations of X and Y were 0.4, so X and Z were 0.4 and 0.35. For this reaction you're given an equilibrium constant. Calculate the concentration of Y. If you're given an equilibrium constant, you need to first of all write an expression for the equilibrium. The expression for the equilibrium constant is Kc equals the concentration of Z divided by the concentration of X divided by the concentration of Y to the power 2. So it's going to look like this. Square brackets mean concentration. Then what you can do is you can rearrange. So I'm going to take Y squared from the bottom on this side to the top on the other side. Then I'm going to divide both sides by Kc and take Kc down onto the bottom on the other side. So now Y squared equals Z divided by X divided by Kc. If you put the numbers in then for Z and X and KC, 0.35 divided by 0.4 divided by 0.29, and then if you square root it, so that's y squared, square root it, y will be 0.55. The student added a few drops of y to the equilibrium mixture, so added more y. How would the colour change? Suggest how the colour of the mixture change. Give a reason for your answer. So they're adding more y. So let's go back to our mixture here. If you're adding more y, by Le Chatelier's principle, it will try and oppose that change and try and use up the y. So if you add more y, by Le Chatelier's principle, it'll try and use up the y, and it'll use up the y by shifting the position of equilibrium to the right hand side, using up the y and making more z. Now it says z is orange in colour, so the colour is going to darken or get more orange. And the reason is the equilibrium moved to the right to oppose the increased concentration of y, to use up some of the y. The student warmed the equilibrium mixture. Predict the colour change, if any, when the equilibrium mixture was warmed. Well, let's have a look back again then. Right, the reaction is minus 20 kilojoules per mole. It's exothermic. That means it's exothermic going in the right to the right. So when you make Z, it's exothermic. In the reverse direction, when you make X and Y, it's endothermic. It would take in heat. So if I provide heat for it, it says here, what would happen when the student warmed the equilibrium mixture, so provided heat. So by Le Chatelier's principle, the equilibrium will shift to try and reduce the amount of heat, oppose the change, and lower the temperature. And it would lower the temperature not by going to the right hand side, that's exothermic, by going to the left hand side and lowering the temperature of the surroundings. These are colourless, therefore the solution would start to fade in colour.